Good morning, everyone. So first of all, I would like to thank Scott for giving me opportunity to give this talk at this conference. And today I'm going to talk about the structure and dynamics of insoluble bismuth oxide-based compounds studied using combination of LDI MS and isotope exchange in situ. So bismuth is a post-transition element from the periodic table, and the element in the periodic table that has the heaviest monoisotopic, that is actually heaviest monoisotopic element. And from chemical perspective, it can form metal oxide-based polymeric compound that all of them which are characterized by low solubility in water-based solutions. And these compounds found multiple applications, not only in electronics and energy storage, but also in medicine and for some pharmaceutical applications. And as far for pharmaceutical applications, one of the best known examples of these compounds is bismuth subsalicylate. So bismuth subsalicylate is a key component of pepto-bismol drug that is used to treatment of different digestive diseases. And this compound is insoluble in water, and despite it is known for over 100 years, its chemical structure have been revealed only in the previous year. And this compound, once it comes to the stomach, it hydrolyzes by the hydrochloric acid into the bismuth oxychloride, the compound that is actually that is known to be the key component for its anti-digestive action, and also salicylic acid. And using these two compounds, bismuth subsalicylate and bismuth oxychloride, we aim to develop mass spectrometry-based approaches for characterize these and other bismuth-based polymeric compounds. From mass spectrometry point of view, the main problem with this compound is that all of them are, as they are insoluble in various solutions, it's very difficult to use different ionization methods that mostly using for solutions. Only those that can work with compounds that can be ionized from the surface are suitable for characterization. And in the 70s, secondary ion mass spectrometry have been used for characterization of bismuth oxide, and several ions containing bismuth and oxygen atoms have been ionized there. In our work, we used alternative approach, and we used laser desorbed ionization. This ionization also can work with compounds that are placed on the surface, and usually it's efficient for compounds that have UV absorbing compounds, and this is good because bismuth is one of them due to its electronic structure. And in several cases, it can also enable fragmentation of large polymeric chain. That is also what we need. So for initial characterization, we used bismuth subsalicylate, and in the first experiments, we were mostly observed only different clusters of bismuth of different size in LDI spectra of bismuth subsalicylate. But once we increase the energy for fragmentation, we observed the presence of the satellite ions in the spectra, and when we annotate the ions, we found that all of them consist of different numbers of oxygens and carbon atoms. And if we will try to map these fragments onto the polymeric structure of bismuth subsalicylate, we can observe that all of these ions derive from the fragmentation, from the cleavage of the polymeric structure of bismuth subsalicylate. Yep. Also, because we know that this compound should convert to the bismuth oxychloride in the presence of the hydrochloric acid, we decided to compare the mass spectra of the bismuth subsalicylate before and after incubation in hydrochloric acid. And in the spectra of the hydrolyzed products of bismuth subsalicylate, we weren't able to observe any ions that have carbons inside, but observe multiple compounds that have bismuth, oxygens, and chlorine atoms. And when we compare the spectra of these hydrolyzed products with the commercially available bismuth oxychloride, we found that they have nearly identical spectra, confirming that this hydrolysis leads to the complete to the the 100% yield of the bismuth oxychloride and salicylic acid as a byproduct. If we look at the structure of bismuth oxychloride, that is also bismuth oxide-based polymer, it can represent it as a sandwich-like structures with multiple layers of the 2D-like polymeric planes where ions of bismuth and oxygen, they assembled into with orthogonal positions. And these layers of bismuth oxide, they are cross-linked by the chlorine atoms, forming this tightly packed rigid structure. And if we again try to annotate the ions now for bismuth oxychloride in positive and negative ion mode, we can find that for bismuth oxychloride in positive mode, we can observe large fragments up to 6 bismuth, 8 oxygen atoms that were directly produced by the cleavage of this polymeric structure. For negative ion mode, the ions are smaller and they have larger number of chlorine atoms, maybe likely serving as charge carriers. And importantly, we weren't able to observe any any complexes that has a stoichiometry that is impossible from the polymeric structure that is known. And it means that we do not have any restructuring of the fragments, and all of these fragments comes from the direct cleavage of this compound after the LDI MS. And in this case, LDI MS is very good because it can get the static snapshot of the structure of this compound in the static way. The main problem is that not only static picture is interesting for characterization of these compounds, but also it's important to assess their structural dynamics, because it's needed to assess the degradation pathways to characterize the stability of these compounds. And inspiring by success of isotope exchange methods in biology for characterize of the structure of the biomolecules, we decided to implement a similar approach for these compounds. The main problem is that because these compounds are insoluble, all isotope exchange reactions need to be performed in the two-phase system with a solid phase. Solid phase is actually bismuth oxychloride, while the liquid phase should be the solution enriched with some kind of isotopes. And we call this approach heterophase isotope exchange analysis in situ. And this approach should have several steps. On the first step, this dry compound should be resuspended in isotope enriched solution. And on the second step, this solution should be incubated for a specific amount of time. Afterward, the solution should be completely dried, and the compound should be placed on the LDI target, and the LDI MS spectra should be measured. And because, in principle, bismuth oxychloride has 3 types of atoms, and because the bismuth has only one monoisotopic element, it's impossible to perform isotope exchange reaction with bismuth. However, there are 2 other options, oxygen and chlorine, and we propose two sets of experiments. So the first set is with isotope exchange of oxygen, and in this case, the solid bismuth oxychloride should be placed in the O18 water and incubated in this water for a specific amount of time. And if isotope exchange happen, this oxygen 18 from this solution should be incorporated into the solid bismuth oxychloride if there is a dynamic behavior. And this what we can probe using LDI MS. In chlorine exchange, first we need to synthesize bismuth oxychloride that has only monoisotopic chlorine, and this compound can be synthesized from the bismuth subsalicylate because we know that it's completely hydrolyzed by the solution. We need to perform this hydrolysis in the presence of only chlorine 35 isotopes. And this solid monoisotopic bismuth oxychloride need to be, in these experiments, placed into the solution with another composition of the isotopes. In this case, even sodium chloride solution that has natural abundance of isotopes, 25% of chlorine-37, is enough to perform isotope exchange reactions. And this chlorine-37 should be incorporated in the solid form of the bismuth oxychloride that we should be able to probe using LDI MS. So, and for this work, I would like to thank my colleague Jean-Bob Hatho, who did a lot of the work with these isotope exchange experiments. First, we performed the oxygen-18 exchange in the presence of the 100 millimolar hydrochloric acid. We performed a set of experiments with the different time points, and for all of these time points, the set of fragments that can be detected is the same. However, if we'll zoom in onto the intensity onto the signals of several bismuth oxide containing ions, we will observe that their isotopic structure changes over the time. And in this change, from the time course perspective, we can detect two phases. On the first minute, there is a strong incorporation, fast incorporation of oxygen-18, and the total percent of incorporation would be around 75%. And after that, there is a gradual increase over the day in our experiments, and the total incorporation raises up to around 90%. And this can be detected from any of the ions that is presented in the spectrum. If we change the pH of the solution, next we'd like to perform this similar experiments but in the neutral solutions. We need to use another buffer to stabilize the pH. And the main problem is that because most of the buffers have labile oxygens that can stabilize the pH around the needed pH range, they can affect the picture of oxygen exchange. And this is why we come up with one of the recently proposed buffers, difluoroethylamine, that has a pK near the pH 7, but doesn't have any oxygen at all. And in the presence of this compound, we perform the oxygen exchange and found that the exchange rate is significantly lower in this compound in comparison with the under this pH in comparison than in acidic pH, suggesting that the process of isotope exchange depends on the pH of the solution. And the total exchange rate was the maximum that we were able to observe is around 20% after around 1 day of incubation. For chlorine exchange experiments, we perform the chlorine exchange experiments with chlorine-37, and in these experiments we measured the spectra in negative ion mode. We also observed that the set of fragments is the same, but the isotopic structure changes for every of these fragments over the time. Here, the end point for incorporation can be, in principle, the maximum end point can be 25%, because our isotopically enriched solution was natural, chlorine containing compounds with natural abundance of the isotopes. And here we also observe incorporation of the isotopes, but the behavior is different. So the first step over the first minute, it's more steeper, and then we have the more faster increase on the second phase of the exchange, raising to around 20% of incorporation of the 25% maximum possible for these experiments. And these experiments were done in hydrochloric acid, and in neutral pH solutions, we also observe that the exchange rate, similar to the oxygen exchange experiments, that the rate is slowing down, and we can detect only trace amount of isotope incorporation on the comparable time scales with the experiments with the hydrochloric acid experiments with acidic pH. However, we found that not only the pH played a key role for isotope exchange rate, but also we perform experiments with bismuth oxychloride that was derived from two sources. The first is those that we synthesized from the hydrolysis of bismuth subsalicylate, and another one, commercial bismuth oxychloride, that is produced by the oxidation of the bismuth chloride salts. And for these compounds, despite their mass spectra are completely identical, the incorporation of the isotope rate, rate of isotope incorporation is significantly different. Here it was done in oxygen-actin experiments, suggesting that not only the pH, but also the morphology for incorporation can play the significant role in the determining of the isotope exchange rate. And because it is known that bismuth oxychloride may exist in the different morphological structures, some of these morphological structures that maybe have larger particles, they should have lower isotope exchange rate due to the solvent accessibility, while the smaller particles that produced after the bismuth subsalicylate have isotope exchange rate that is higher. So this summary of the work that we did. So we have developed the approach combining of LDI MS and heterophase isotope exchange to characterize of different bismuth containing polymers. And in my last slide, I would like to thank my colleagues, my advisor, for helping for developing of these approaches and conducting this work. Thank you so much.
Any questions?
I don't know if I need the microphone, but have you considered using MALDI and using a matrix to ionize these things?
We haven't, to be honest, we haven't considered to use MALDI, because for MALDI, usually you need to have the formation of the mixed crystals of your compound and matrix. But because these compounds are insoluble, they cannot create these mixed structures with the MALDI matrices. And thus, we don't think that it would be reasonable to do this. Moreover, from the technical point of view, because you have the mixture of matrix and your compound, and once you shoot the laser, you won't be able to distinguish MALDI and LDI, because both of them are absorbing UV light. In principle, in some cases, it may help for compounds that are not ionized, but across the all bismuth-containing compounds that we have characterized, all of them produce very good spectra, even with LDI mode.
There was quite a bit of work that was done with solid phase mixtures and matrix, and I don't know, we could talk after I've done some work with.
Close proximity to each other. They don't have to be crystals, but close proximity, it'll ionize, and you can get to work on UC stuff that lasts around 5,000 to 6,000 by this.
For our cases, the main motivation was that we don't need this.
But I think it was trying to compare just to see was there any energy being put into work stuff up.
Kind of extending on that question, did you expose these to multiple pulses? Are you seeing sample damage with time? Does the spectrum change?
So if we for these experiments we used commercial MALDI mass spectrometer, and after multiple pulses, if you don't put the significant amount of crystals and you shoot them with laser, after several pulses there will be no signal, so the signals completely burn out the sample.
Okay, well, let's thank Daniil.